Lesson 17, Simple Harmonic Motion and the Pendulum. We'll start with an introduction to simple harmonic motion. For this lesson, we'll abbreviate the phrase simple harmonic motion with the letters S, H, M. An object undergoes simple harmonic motion if both of the following are true. The object or particle is vibrating with a constant frequency or period of motion. This means it's going back and forth in some kind of way. There also needs to be a restoring force. A force needs to be something that pulls it back towards the central point. We call this central point the equilibrium point. It's the place that the object would stay at if it didn't have anything pulling it backwards and forwards. Simple pendulums and vibrating weighted springs both exhibit simple harmonic motion since they vibrate, swing, oscillate, or cycle with a regular pattern. A pendulum is an object that hangs from a string and swings back and forth. A swing on a child's swing set is an example of a pendulum. The center point that the pendulum swings back and forth through is the equilibrium point for the pendulum. A spring system is when you take a spring and you put a mass on the end and then you pull it. As a result of the pull, the spring pulls the mass up, back and forth, up and down. The center point for the spring, where it would sit if it were not compressed or stretched, is called the equilibrium point. We're going to do a brief review of the concepts of period and frequency. Period is the time an object that is repeating its motion takes to complete one swing, vibration, bounce, cycle, or oscillation. Frequency is the inverse of period. Frequency is the number of swings, vibrations, bounces, cycles, or oscillations that occur in 1 second. The symbol for period is T, and its unit is the second. The symbol for frequency is F, and its unit is the hertz. Also recall from earlier lessons, the formula period equals 1 over frequency. So if we have an object undergoing repetitive motion like circular motion or an object traveling back and forth, the period is the time for one cycle or once around. The frequency is the number of cycles or times it goes around in 1 second. Here's an example. What is the period and frequency of a vibrating spring that requires 4 minutes and 40 seconds to complete 500 complete oscillations? The total time given is 4 minutes and 40 seconds. This is 4 minutes times 60 seconds in a minute plus 40 seconds, which gives us a total time of 280 seconds. The period is the total time divided by the number of cycles. This will give us the time for 1 cycle. This is 280 seconds divided by 500 complete oscillations, which gives us a period equal to 0.56 seconds. The frequency is the inverse of the period. It's 1 over the period. This is 1 over 0.56, which gives us a frequency equal to 1.79 hertz. The simple pendulum. One day, many years ago, Galileo watched a candle chandelier, or a simple pendulum, swinging back and forth on a long chain in a cathedral. Galileo started to wonder what determined the period of the pendulum. What is the effect of changing the length of the chain? If the mass of the chandelier was changed, would that affect the period of vibration? and if the amplitude or size of the swing was increased or decreased, would the period be affected. Galileo is said to have done most of his measurements and experiments using his pulse as a stopwatch. Galileo found that the pendulum's motion depends on the length of the pendulum, but it does not depend on the mass or amplitude. Amplitude means the maximum displacement of the swing. The period of a pendulum can be calculated using the formula period equals 2 pi root L over G, where the period is given by capital letter T measured in seconds. L is the length of the pendulum's string measured in meters, and G is the acceleration due to gravity and on Earth, the acceleration due to gravity is generally accepted to be 9.81 meters per second squared. So, if you want to know the period of a pendulum swing, you only need to know the length of the pendulum's string and the acceleration due to gravity where the pendulum is located. For example, if a pendulum is 80 centimeters long, what is its period and frequency of vibration? This is a length of 80 centimeters, which is 0.8 meters. The period is equal to 2 pi root length over G, which is 2 pi times 0.8 divided by 9.81, which gives us a period equal to 1.79 seconds. The frequency is the inverse of the period. This is 1 over 1.79, which is 0.5757 hertz. Final example. On a planet called Trathalamore, Billy found a 50-centimeter pendulum completed 20 swings in 33.6 seconds. What is the acceleration of gravity on Trathalamore? Ignoring the fact that Billy traveled all that way through space to conduct a pendulum experiment, we're going to calculate G on this planet. The length of the pendulum is 50 centimeters, which is 0.5 meters. The pendulum's period needs to be calculated as well. This would be the total time divided by the number of swings or the number of cycles, or 33.6 seconds divided by 20 swings gives us a time equal to 1.68 seconds per cycle, or a period of 1.68 seconds. Now we're going to find the G value on the planet. The formula for the pendulum is period equals 2 pi root L over G, and we need to rearrange this for G. The first thing we do is square both sides to get rid of the square root. This gives us period squared equals 2 squared is 4, pi squared is pi squared, and the square root drops away because we squared both sides. Now we can rearrange for G. G equals 4 pi squared L over T squared. So, G on the planet is equal to 4 pi squared, the length of the string, divided by the period squared. This gives us a G value on the planet of Trathalamore of 6.99 meters per second squared. Resonance. Imagine pushing a child on a swing. A swing is really just a special kind of pendulum system. How do you make the child go higher? Well, if you push the swing randomly or out of sync with its pendulum motion, the child will never go very high. However, if you make sure that you time your pushes so you push in sync with every time she swings back at you, the simple harmonic motion of the swing will have an increasing amplitude, and she will go higher and higher. We call this kind of in-sync force on a pendulum system resonance. Mechanical resonance. Once you get the child on the swing moving, it's really easy to help her maintain her swinging motion. That's because all that is needed to replace that little bit of energy that is being lost due to friction. As long as your forced frequency exactly or closely matches the resonant frequency of the swing, it will continue to go higher very easily. In fact, if the two match exactly, then the amplitude of the swing can become very large. Like a pendulum swing, some engineered structures and natural systems have distinct resonant frequencies. These are the frequencies that they vibrate at naturally. Mechanical resonance is the tendency of a mechanical system to respond at greater amplitude when the frequency of its oscillations matches the system's natural frequency of vibration than it does at other frequencies. For example, you might have heard someone singing to break a wine glass. It is recorded of having been done once, and that singer didn't have to sing loud. She just sang at a forced frequency that matched the resonant frequency of the glass. Another example is the Tacoma Narrows Bridge disaster. This is a modern-day example of resonant frequency. The bridge fell apart because the winds blowing across it matched its natural resonant frequency. Examples such as this, where there is an exact match, are referred to as mechanical resonance. Mechanical resonance is a very real concern for people designing and building large structures. If it is not taken into account, then the entire structure could collapse. Sometimes if you're standing still in a large building, you might feel these vibrations momentarily.